structured compression by the weight encryption for unstructured pruning and quantization. Effect. More compression techniques such as pruning and quantization have become increasingly important to reduce the memory footprint and the amount of the computation. Despite model size reduction, achieving performance enhancement on devices is, however, still challenging, mainly due to the irregular representation of sparse-matrix format. This paper proposed a new weight representation scheme for sparse quantized neural networks, specifically achieved by the fine-grained and unstructured pruning method. The presentation is encrypted in a unstructured regular format, which can be efficiently decoded through XOR-gate-network during inference in parallel manner. In demonstration, various deep learning models that can be compressed and represented by our proposed format fixed and high compression ratio. For example, for fully connected layers of AlexNet on the ImageNet dataset, we can represent the sparse weight by only 0.28 bits per weight for 1 bit quantization and a 91% pruning rate with a fixed decoding rate and full memory bandwidth usage. Decoding through XOR-gate-network can be performed without any model accuracy degradation with additional patch data associated with the small overhead. Introduction. Deep neural networks (DNNs) are evolving to solve increasingly complex and varied tasks with a dramatically growing data size. As a result, the growth rate of model sizes and recent DNNs leads to a slower response time and higher power consumptions during inference. To mitigate such a concern, model compression techniques have been introduced to significantly reduce the model size of DNNs while maintaining the reasonable model accuracy. It's well known that the DNNs are designed to be over-parameterized in order to ease local minima exploration. Thus, various model compression techniques have been proposed for high performance and/or low power inference. For example, pruning techniques remove redundant weight to zero without compromising the accuracy in order to achieve memory and computation reduction in devices. As another model compression techniques, non-zero weight can be quantized to fewer bits with the comparable model accuracy of full precision parameters as discussed in. To achieve even higher compression ratio, pruning and quantization can be combined to form a sparse quantized neural networks (SQNNs). Intuitively, quantization can leverage parameters pruning since pruning reduces the number of weights to be quantized and the quantization loss decreasing accordingly. Decompression ternary weight network (TWN) and trained ternary quantization (TTQ) and Viterbi-based compression and present recent efforts to synergistically combine pruning and quantization. A bit benefit from the sparsity. It's important to represent pruned models in the format with a small memory footprint and implement fast computation with the sparse-matrix as input operand. Even if the reduced SQNNs can be generated with a high pruning rate, it's challenging to gain a performance enhanced without inherently parallel sparse decoding process during inference. To illustrate such a challenge, Figure 1 presents the DRAM bandwidth and the number of transaction and execution time of the metric multiplication using one random 2048 by 2048 sparse matrix following CSR format and a random 2048 by 64 dense matrix in NVIDIA Tesla V1 supported by CUDA 0.9.1. Because of the unbalanced workloads, Note that the pruning each weight is somewhat independent and a random operation, and the additional data for index sparse matrix computations using CSR format do not offer performance gains as much as disparity. Moreover, if the pruning rate is not high enough, sparse matrix operation can be even slower than a dense matrix operation. As such, unstructured and block-based pruning techniques for DNNs had been proposed accelerated decoding of the sparse matrices using reduced indexing space, as figure 2 shows. However, coarse-grained pruning associated with the reduced indexing space exhibit relatively lower pruning rate compared to unstructured pruning, which marks the way with the fine-grained granularity. In conventionally sparse matrix format representing unstructured pruning, that is, random weight can be pruning. Decoding the time can be vastly differ if the decoding processes are conducted in different blocks simultaneously, as shown in the conventional approach in figure 3. To enable inherently parallel computation using sparse matrices, this paper proposes a new sparse format. Our main object is to remove all pruned weights such that the resulting compression ratio attracts the pruning rate while maintaining a regular format. Interestingly, in VLSI testing, proposal for test data compression had been developed from a similar observation. That is, there are lots of don't care bit pruned weights in the case of the model compression, and the locations of such don't care bits seems to be random. The location of the unstructured pruned weights also seems to be random. We adopt exclusive XOR-gate-network previously used for test data compression to decode the compressed bits in a fixed rate during inference, as shown in figure 3. XOR-gate-network is small enough such that we can embed multiple exclusive XOR-gate-network to fully utilize memory bandwidth and decode many sparse blocks concurrently. Correspondingly, we propose an algorithm to find encrypted and decompressed data to be fed into exclusive gate network as input. Related works and comparison. In this section, we introduce two previous approaches to present sparse matrices. Table 1 describes the CSR format, bit-to-bit based index format on our proposed method. The compressed sparse low decompression utilized the compressed sparse low CSR format to reduce memory footprint on devices. Unfortunately, CSR format, including the blocked CSR, representing irregular data structures not readily supported by the high parallel computing systems such as CPUs and GPUs. Due to the uneven sparsity among rows, computation time of algorithms based on a CSR is limited by the least sparse row, as illustrated in figure 3. Although suggested hardware support via a large buffer to improve load balancing, performance is still determined by the lowest pruning rate of the particular row. In contrast, our scheme provides a perfectly structured format of weight after compilation, such that the high parallelism is maintained. Bit-to-bit approaches. Bit-to-bit based compression attempt to compress pruning index data and quantized weight with a fixed compression ratio using a don't care bit, similar to our approach. Quantized weight can be compressed by using the Vivat algorithm to obtain a sequence of input to be passed into a bit-to-bit encoding 1 bit by the cycling. Because only 1 bit is offsetted for each bit-to-bit encoder, only an integer a number of bit-to-bit encoder outputs is permitted to add the compression ratio, while our composed scheme allows any rational numbers. Because only 1 bit is used as input for a bit-to-bit encoder, bit-to-bit based approach just require large hardware resources. For example, its memory allows 1024 bits per cycle of bandwidth and 1024 bit of encounters are required, where each bit of encounter entails multiple flip-flops to support sequence detection. On the other hand, our proposed scheme is too resource efficient to support a large memory bandwidth because the flip-flops are unnecessary. 3. Proposed weight representation for structures compression. Test data compression usually generates random numbers as the output using the input data as seed values. The output, the test data containing the don't-care bits, can be compressed successfully if the such output can be generated by the random number generator using at least the one particular input seed data, which is compressed to test data. It's well known that the memory reduction can be high as the portion don't care bits. If the randomness is good enough, test data compression and the SQLs with the fine-grained pruning share the following properties. Primary pruning induces don't care values as much as pruning rate, and if the weight is unpruned, then the quantization bits are assigned to 0 or 1 with equal probability. In this section, we propose a new weight representation method exploiting such shared properties while defeating the high memory bandwidth requirement and the lossless compression to maintain the accuracy. 3.1 Encryption and Decryption. We use an XOR-gate-network as a random number generator to do it. Simple design and a strong compression capability. Such a generator is not a desire for a test data compression because it requires too many input bits. Suppose that real number weight matrix W is quantized to be binary matrix WIQ. I is greater or equal to 1 and less than or equal to NQ, with NQ as the number of bit quantization. As the first step of our encryption algorithms, we reshape each binary matrix WIQ to be a 1D vector, which is evenly divided into smaller vector sequences of the n out size. Then each of the evenly divided vectors WQ is including the don't care bits is encrypted to be a small vector WC of NIN size without any don't care bit through the exclusive OR-gate network. Each encrypted vector WC is decrypted to be the original bit consisting of the correct care bits and the randomly filled don't care bits with respect to WQ. Figure 4 illustrates the encryption and the description and provide procedure example using a weight matrix and a 4D tensor. For example, conv layers can also be encrypted through the same procedure after flattening. The structure of the exclusive gate network is fixed during the entire process and is depicted in figure 5 can be described as a binary matrix M over the Galois field with the two elements GF2 using the connectivity information between the two input vectors WC and compress the encrypted weight, and the WQ is note that the M is still predefined and designed in a way that each element is randomly assigned to 0 or 1 with the same probability. We intend to generate a random output vector using a seed vector WC while targeting as many care bits of WQ as possible. In order to increase the number of the successfully matched care bits, an exclusive OR-gate network should be able to generate various random output. In other words, when the size of the scenes vectors and output vectors are given n1 and n output irrespectively, all possible to n output need to be well distributed in n out solution space. Before discussing how to n in and n out, let us first study how to find the vector wc and w given wq as shown in the figure 5. The overall operation can be expressed by the linear equation m net w over the gf2, and note that the linear equation are associated with don't care bits in the wq can be ignored, because the description through the exclusive gate network can be produce any bits in the location of the don't care bits. By deleting unnecessary linear equation, the original equation can be reduced as below. As a for example, since only 4 care bits exist in figure 5 and 4 by 8 by 4 matrix M is reduced to a 4 by 4 matrix, and by removing first and second and sixth and eighth rows, given the pruning rate as WQ contains n out is the n minus x care bits on average, assuming that the n out and the x minus equation are independent and non-trivial, the required number of seed inputs can be small as n out times n minus s, where in the compression ratio of n out over n1 becomes n over n minus 1. As the result, the higher pruning rates lead to a higher compression ratio. However, note that the linear equations may not have the corresponding solution where there are too many local care bits or there are conflicting equations for given vector WQ. 3.2 Extra patches for lossless compression. In order to keep our proposed SQN when represent lossless, as we add extra bit to the correct unavoidable errors. That is patching. Unsolvable linear equation implies that an exclusive random number generator cannot produce one or more matched care bits of the W. To resolve such an occasion, we can replace one or more care bits of WQ with don't care bits to remove conflicting linear equation. As depicted in figure 6, we recall the location of the replacement as detached, which can be used to recover the original care bits of the W by flipping the corresponding bits during the encryption. For every WQ, and patch indicate the number of the replacement for each WC. Since n patch is always scanned prior to the description using the WC, the same number of bits is reserved to present the n patch for all encrypted vectors in order to maintain a regular compressed format. On the other hand, the size of the patch can be different for each WQ. Overall parallelism is not disrupted by the different patch sizes, as flipping occurs infrequently. At the expense of the n patch and d patch, our compression techniques can reproduce all care bits of the WQ and therefore does not affect the accuracy of the DNN models and the obviated retraining. In sum, the compressed format include, like this expression, encrypted first expression encrypted from the quantized weight max through this expression, and 2 and patch and 3 d patch. And the result compression ratio R is like this, and while PJ is the jth n patch and P blah blah blah, improving the R is enabled by the increasing the n out and the n in, and decreasing the amount of the patch. We introduce a heuristic patch searching algorithm to reduce the number of the patches while also optimize n in and n out. 3.3 Experiment using synthetic data. An exhaustive search of the patches requires exponential complexity, even though the search method minimizes the number of patches. Algorithm 1 is heuristic. Algorithm 2, right? A search encrypted bits including the n patch and the d patch, and WQ in W. The algorithm is incrementally enlarged induced in linear equation by including a care bit only when a large equation is still solvable. Note that the remark R reference in the algorithm 1 generates a reduced low column form to the quickly verifying the linear equation is solvable. If adding a certain care bit makes the equation observable, when a don't care bit take its place, and the M patch and T patch are updated accordingly. Although the algorithm want to yield more replacement of the care bits that exhausted search by up to 10% from by extensive experiment, our simple algorithms had a time complexity of O and R, which is much faster. To investigate the compression capability of our composed scheme, we evaluate a large random weight matrix of the 10,000 elements where each element becomes a don't care bit with a probability of the 0.9 sparsely of the pruning rate. If the element is a care bit, then a 0 or 1 is assigned to with the same probability. Note that the randomness of the location don't care bits is a feature of the fine-grained pruning method and assigned to 0 or 1 to weight with the same probability obtained using the well-balanced quantization techniques. When n is fixed, the optimal NR maximized the memory reduction offered by the algorithm 1. Figure 7 plots the corresponding memory reduction from the WQ on the right axis and the amount of the WC, and the N patch plus T patch on the left axis across the and a range of the NR values when NI in 20. From figure 7, it is clear that there is a trade-off between the size of WC and the size of the M patch and T patch, and the increasing N out rapidly reduces WC, and while M patch and T patch grow gradually. The highest memory reduction, 0.83, is achieved when N out is almost 200, which agreed with the observation, and the maximum corresponds is constrained by the relative number of care bits. Consequently, the resulting compression ratio approaches 1 over 1 minus s. Given the relationship of the, we can now omit the N1. Figure 8 compares memory reduction for various NR across the different values of Ni. The resulting trend suggests the higher N1 and in the yield more memory reduction. This is because the increasing the number of bits used as seed values for exclusive XOR-gate random number generate enables a large solution space, and as a result, fewer D-patch are needed as N1 increases. The large solution space is especially useful when the care bits are not evenly distributed throughout WQ. Lastly, N1 is constrained by the maximum computation time available to run algorithm 1. Figure 9 is representing a relationship between the pruning rate S and the memory reduction when an N when it is 20 is sweeping S. Since the high pruning rate translates to fewer care bits and relatively fewer D-patch, figure 9 confirms that the memory reduction reaches S and S increases. In other words, the maximum pruning rate is key to compression quantized weight with a high compression ratio. In comparison, ternary quantization usually induces a lower pruning rate, and our proposed representation is best implemented by the pruning first to maximize the pruning rate and the quantizing the weight. Okay, X4 experiment on various SQNNs. In this section, we show the experimental result of the proposed representation for our four popular dataset: MNIST, ImageNet, Cypher10, and Pan Tree Bank. Through the compression ratio ideally reaches 1 over 1 minus s. The actual result may not, because don't care bits can be less evenly distributed than a synthetic data we used section 3.3. Hence, we suggest several additional techniques in the section to handle uneven distribution. which are proven by the mask layer generated by binary index matrix factorization after pre-training and retrained. Quantization is performed by the following the technique proposed in 2015. The where quantization or homage is performed based on the quantization method from the number of the bits per date weight required by our method is compared with the case NQ in bit quantization with the additional 1 bit indicating pruning index. For region ternary quantization consists of the 1 bit quantization and 1 bit pruning indication by per weight. We first tested our representing using the LUNA5 model at MNIST. LUNA5 consists of the two conventional layer and the two fully connected layers. Since the FC1 layer dominated the memory footprint 93%, we focus only the FC1 layer whose parameters can be pruned by 95% with the proposed method. FC1 layer is effectively represented by the only 0.19 bits per weight, which is 11 times smaller than the ternary quantization as figure 10 shows. We also tested by proposed compression techniques on the large-scale models and the dataset, namely arXiv image dataset. We focused on the compressing FC5 FC6 fully connected layers occupying 90% of the total model size of the ArXiv. Both layers are pruned by a rate of the 91% using the binary index matrix factorization and compressed by the 1-bit quantization. The high pruning rate lets us compress the quantized weight by the 7 times. Overall, FC6 and 5 and 6 layers, 5 and 6 layers for ArXiv requires only 0.28 bits per weight, which is substantially less than 2 bits per weight required by ternary quantization. So we further verified the compression technique using the losslessness 32 on the Cypher-10 dataset in the baseline accuracy of 92.5%. The model is pruned and quantized to 2 bits, reaching 91.6% accuracy after retraining. A further compression with our proposed SQNN format yields 1.22 bits per weight, while 3 bits is required without our proposed compression techniques. Additional on RNN models with the LSTM layer size 300 on the PTB dataset with performance by the using perplexity per word is compressed by the representation. Following our proposed representation scheme along with the pruning and the 2-bit quantization such as PTB LSTM model requires only 1.67 bits per weight. For various types of layers, our approaches techniques supported by the weight disparity provide additional compression over ternary quantization. The compression ratio can be further improved by the using more advanced pruning and quantization method. For example, since the principles of our compression method do not rely on a specific pruning and quantization method used. The 5 discussion. 5.1 Variation in execution time. While description processing through the exclusive XOR-gate-network provide a fixed out rate, thus the high parallelism, if all mismatched bits are supposed to be corrected by patches, then the entire encoding, decoding, including the description and the patch correction, may result in a variation in execution time due to the irregular patch size. In order to mitigate the variation in patch process, we first assume that patch data structure decoupled from the encrypted weights, such as the message given a small stream data to be stored in buffers in a fixed rate. Then, for each exclusive encryption cycle, the patch as much as patch is read from the buffer to use the fixed exclusive output. The figure 11, the patch is stored into loaded from FIFO buffers when the number of FIFO banks is n FIFO. If dpatch is needed, FIFO buffers deliver dpatch to the patch process logic, while available dpatch throughput for load store is determined by the number of the FIFO banks. Decoding the process can be stored when the FIFO is either full or empty, as in temporary dpatch consumption rate is too low or too high. Figure 12 presents relative execution time using cs.LG format or the proposed scheme with different N5 configuration. FIFO size can be small enough, say 256 entries, to tolerate temporal high peak dpatch uses. Hence, the figure in figure 12 stores in the proposed scheme are due to high dpatch throughput demands along with a large M-patch. Note that the CSR format yields high variation in execution time because each row exhibits various numbers of unpruned weights. On the other hand, in the case of a proposed scheme, increasing N5O at the cost of additional hardware design enhanced dpatch throughput, and the third, reduce the number of the store secured by defeat by the ban of FIFO in some region. A FIFO size significantly reduces execution time variation, which has been a major bottleneck in implementing fine-grained pruning schemes, as demonstrated in Figure 1. The 5.2 Practical Techniques to Reduce M-patch. If the N output is large enough, patching overhead is not supposed to disrupt parallel decoding ideally. However, even for a large N out, if the non-uniformity of the pruning rates is observed over a wide range with the matrix and patch, may consider the increase. The large M-patch then the region not only degraded compression ratio compared with the synthetic data experiment, but also the tolerated the parallelism in the debugging process. The following techniques can be considered to reduce the N-patch. The blocked N-patch assignment. The compression ratio R in the equation 8 of the section 3.2 is affected by the maximum of the blah blah P1 to PL. Note that the particular vector W may have an exceptionally large number of care bits. In such a case, even a quantized matrix WQ consists of mostly don't-care bits and a few patches are needed. All of the compressed vector WC must employ a large number of bits to track the number of patches. To mitigate such a problem to enhance the compression ratio R, we divided the binary matrix WQ into several blocks. Then a max P is obtained each block independently. May different N is assigned to each block to reduce the overall M-patch data size, minimizing the M-patch for the small N1 and in. As one simple patch, minimizing the algorithm used to list all possible to N in input for WC and corresponding output throughput M plus on a memory of the particular WC that minimizes the M number of the patches. At the cost of the high space complexity and memory consumption, such as exhaustive optimization guarantees minimized M-patch N1 and in below 3 thoroughly is a practical value. Okay. Conclusion. This paper proposed a compressed representation for sparse quantized neural networks based on an idea used to test data compression. Through XOR-gate-network and solving linear regression, we can remove both don't-care bits and quantized models for further compression by sparsity Since our representation provides a regular compression weight format that affects the high compression ratio, SQNN enables not only memory footprint reduction, but also inference performance improved due to the inherently parallelizable computations. Okay, from the reference 1 to 29 and 27. Thank you for your time. It was unstructured compression by the weight encryption for unstructured pruning and quantization. Thank you. See you next time.